All right, thank you. Thank you for invitation. It's very nice to come here. Very beautiful place. I hope that I'm heard now. I did move it, this thing. Okay, so I will start with describing the setting just to set the notation. So I will start the setting of things that will happen. So I'll have X. It's a complex analytic manifold. And I will consider functions of various kinds. I will consider the real valued functions, then smooth complex valued functions, and then, of course, also holomorphic functions inside. And then correspondingly, I will have the breaking up of the forms into the holomorphic and anti-holomorphic parts. So this is just the third part of the setting. The second part will be the some smooth bundles. So E, this letter will always, now in my talk will be a C infinity bundle. Oh, vector bundle. On X and over complex numbers. So all of my bundles will be with complex coefficients. And now if I will be thinking about holomorphic structure, so if it's a holomorphic bundle, I will use notation like this. So E will be a holomorphic bundle with the same underlying E. All right, and then I will, as in the talk, it says there will be connections. I will write a lot of connections. So I'll have a connection breaking into the holomorphic and anti-holomorphic part, and then this connection, the anti-holomorphic part, gives you the holomorphic structure. Then in the last bit of notation, I will have a Hermitian metric. H. And it will be positive definite. And then I will consider H connections. So in other words, connections such that dH is 0. So it's constant with respect to the connection. Okay, so I will start with some very basic, almost obvious facts. That I can say immediately in the setting is that if I start with a holomorphic bundle and a Hermitian structure, then from that I can have exactly one connection, H connection, satisfying the condition that the anti-holomorphic part in the holomorphic frames will be exactly the Dolbeault differentials. In other words, this is the Chern connection. So if I start out with holomorphic structure and Hermitian structure, then I will have something. I'll have a unique connection corresponding to holomorphic structure and Hermitian structure, and that's a very simple fact. And then another one, even simpler, is that for such connections, if I have the anti-holomorphic part being given by the Dolbeault, then of course, and it is Hermitian, then both the holomorphic and anti-holomorphic part of the curvature vanish. So that means that we have that curvature of such connection is a 1-1 form. Okay, so that's, of course, all very simple, and mostly just to introduce the names and the notation. And now I will go to some special case. And I will look at a special holomorphic bundle on X, namely the tangent bundle. It has a canonical homomorphic structure, but now from that, I'll have that I have the turn connection, the uniquely defined turn connection. If I have add to that Hermitian structure. So here I will denote it, because it is on a special case, I will denote it by G. To separate this will remain constant all the time because it belongs to the manifold itself. Now, if I have this, then from that I will have the Chern connection on the tangent bundle, and because it is a tangent bundle, that's the part that special about it is that I can ask, does it have a quotient? And then the familiar definition, I was told that I need to the first hour I need to give simple facts. So here it is, familiar definition, that this xg is scalar if this Chern connection on the tangent bundle has no torsion. So, question: should I skip all things like this, or is it the right things to say, or is it too much? Because I don't know how detailed I should be. So that was or you cannot just note. So should I be faster, or is it okay? It was okay. Good. All right. So now I introduce that again mostly because I will be staying in the world of scalar manifolds. So from now on, X becomes just scalar manifold, and I will not say that anymore. But there is another characterization of scalar manifolds. Just probably even more familiar, is that I can introduce a fundamental form, which I take locally. If I take this metric, the Hermitian metric, which is of course not completely bilinear; it's only sesquilinear, and then here I multiplied by I. So I use I as not as an index, but root of -1. Then this becomes a two form, and then if so, xg is scalar if and only if omega is closed. Well, if omega is closed, and I said that I assume that it's all scalar in my world, then I can look at the class, the cohomology class in the RAM cohomology of this scalar form, and then I can ask, is it integer or not? So if is integer class, then there's a theorem that says that then the manifold is in fact embeddable into projective space. Then X sits inside projective space. And there is another fact again. So I'm still in summarizing everything. Another fact that's any such projective manifold is actually algebraic. So X is an algebraic variety, or is amorphic to algebraic variety. And once again, I assume this to happen. So it's not only that I assume X to be scalar, I assume that it is actually an algebraic manifold. And now, yeah, so actually I would like that to be closed, yes. So I didn't say that from the beginning, but I assume X is compact. do not consider things that are not compact. I mean, I could for a long time, but at some point I stopped.
Be problematic with this.
Yes, yes, yeah, obviously. Yeah. So yeah, if it is well, it depends on how you extend the notion of variety. You can also say that's quasi-projective.
Yes.
Hmm?
There's no way the unit is different, right?
Okay. No. Okay. Yes, you're right. I mean, one way. Yeah.
Yeah.
You're right. So that is for that part, for the second fact. So for the last fact, that's algebraic right. Okay. So now that is the stage, and the story actually begins with actually choosing connections on E. And so we have two constructions that are described here. And again, they are very simple. So if I start with smooth bundles with Hermitian structure, then I can choose H connection such that it squares to 0, and that gives me a holomorphic structure. That gives me E. If I start with E, I can choose H, and then I'll have a Chern connection. So on one hand, we have connections. On the other hand, we have homomorphic structures, and everything is somehow with the background, with the Hermitian structure in the background. And now I would like to elevate this simple things from here to correspondence between moduli spaces, and that means that I need to take into account equivalences. So now the goal is to take equivalences into account. So that would allow me then to consider moduli spaces. So moduli spaces, as always, they're constructed by looking at all those things that we like, satisfying all the equations that we want, and then dividing by the equivalences. And now there is an issue that we have to take care of here. And I will describe this issue in by way of example, because I will use that example later. And this example is the following. I'll start something, again, very simple. I'll look at the linear maps over C. So it's linear homomorphism of two vector spaces, CK and CN. And then I can act on this space from the right by the GLK. And then act on this by GLKC. So I'm rotating things inside on changing things inside the domain. And now when I try to divide by it, so trying to divide by this action, and then the result is not satisfactory. So here, what I will have is in a particular example, so let's say k equals to 1 and n equals to 2. So then I will have C2, and I would like to divide, in this case, by C multiplicative. And then what I will have here is just a point. But that's not what I actually want to have, because here the problem is that orbits of this action here, there are big orbits, and then there's one special orbit which is in the closure of every orbit. So 0 is in the closure of every orbit, which means that simply dividing by it is not a good idea. So this, in fact, will be the categorical quotient, and the map will be algebraic. So it is really affine varieties and affine map. Everything is good, but it is not a geometric quotient. So this is not a geometric quotient. Now, geometric quotient is a good quotient like this, but with the additional condition that fibers consist of only one orbit each. So here comes the idea of GIT. If you have a situation like this, then what you do is that you isolate the problem. So you remove the orbit that is an inclusion of every other orbit, keeping only those things that are good. So restrict to a good part. Well, here it is not in the technical meaning. So this is a good quotient in the technical sense, but it's not geometric. Now here good is not in the technical sense, to a good part. And then obtain, of course, C2 without the origin divided by, and that is P1. If I do it here, well, let's see how slow I am moving. What will I get if I have you seen what will happen if I try to do the same in the for situation k larger than n, larger than 1? Larger than n is not interesting, of course, but larger than 1. What? The Grassmannians, yes. So then in general, I get from here the Grassmannians Kn. And that's actually an important fact. So a good example of when stability appears is that you can construct Grassmannians simply by looking at the stable points and the action there. I will not talk much about semi-stability. Here, in this case, semi-stability implies stability, so everything is very simple, and everything is closed, and then you get a projective scheme as a result. Okay, yeah. Well, closed points. Yeah. So I'm really talking about varieties. So the idea of that's not. Okay, so here then, of course, what we do by restricting to a good part, restricting to a stable part, stable point. So now here we are back to the technical meaning of the words, and then of course, if I would like to replicate some kind of construction here, so on the part of the holomorphic bundles, I can do that. In fact, I can do it for coherent sheaves, and there we have a very elaborate theory of stability that I will not touch at all. And I will now would like to say something about what can be done, what is done on the gauge-theoretic side. So what happens there in terms of stability? And for that, I need to have the following definition. So I'm back to the situation out of this example, back to the situation of bundles and Hermitian structure and curvature. So we have E, H. So this is not a homomorphic bundle, but it has a Hermitian structure. And then we have the connection D, and then R. So let R be the curvature. Actually, I will put it F. Be the curvature of D. And now the part of this definition is I define the mean curvature to be the this one. This comes from one of those operators that you have on Kähler manifolds. So this comes from the Kähler form, or in other words, equivalently, that if you take K multiplied by, so K is of course here, this is a two form, that would be a two form values and endomorphisms. So this will be just zero forms with values and endomorphism. So this will be top forms with values and endomorphisms, and that's nothing other than just INF n minus 1, where n is the dimension of X. Okay. And so now I can finally give the most important definition that I think was in the title of my talk, that if K, which is just a section of the endomorphism bundle, is equal to phi identity, where phi is a constant number, then D is called, so remember K is the mean curvature, D is called a Hermitian-Einstein connection. So the Hermitian part is then where we have the preservation of the Hermitian structure. The Einstein part is this here.
Different definition of K that you're saying.
No, it's one and the same definition. So just wait to write it. So if again, I don't know which symbols I can use freely. So I don't know how much Keller geometry is very well known. So instead of lambda is the operator. If you haven't seen, I'm sure you have seen wedge product. That's all. I just wrote the same thing twice. Okay, so now here I would like to make a remark, which is important for the rest of the talk. Suppose that we have that D is a Hermitian-Einstein connection. What can we say about this number phi? Now, if D is Hermitian-Einstein, then phi depends only on the homology class of our Keller structure, on the first Chern class of our complex bundle, and in particular, that's it. That's all it depends on. In particular, if the first Chern class is 0, then this phi is not just a constant number, it is constant number 0. And that would be, again, important for me in the future. So I will not need to worry too much about particular numbers. I'll just assume that something is 0. Okay, so here comes this big theory, or big theorem, or several theorems grouped in one name. And I will just quote this theorem, and this is extremely important. And it was proved by Donaldson, Uhlenbeck, and Yao. And what it says is the following, that if we start with our complex bundle E with Hermitian structure, and we look at all Hermitian-Einstein connections, well, these Hermitian-Einstein connections in particular will give us holomorphic structures, but moreover, they will give us stable holomorphic structures on E. And this correspondence is, so here E and H are fixed. And this is a bijection. Okay? So this is, since we think about holomorphic bundles, or we can also think, because our, as I said, I assume that X is algebraic. I can think about algebraic bundles. So here I can think about algebraic, stable algebraic bundles on my algebraic variety, which is smooth. Here I have something about involving connections and conditions on the curvature, specifically on mean curvature. And it turns out that it's a bijection. Moreover, it's not only a bijection, it's also an isomorphism of real analytic manifolds. So analytic isomorphism. So this is, of course, requires putting structures of analytic structures on both sides. So here, of course, we have a moduli space of stable bundles and moduli space of stable connection. So the Hermitian-Einstein condition is the stability condition, and then the stability conditions turn out to be in correspondence. Okay, so I say gauge theory quite a lot. What does it have to do with gauge theory? So here we have a definition. So notice that in this correspondence here, what we have is we start with a homomorphic structure or algebraic structure. We start with let's call it algebraic structure, and then we produce something which is a connection on this Hermitian structure here. But instead, what we can do is actually to find the Hermitian structure here together such that the Chern connection will be satisfying the conditions, and then switch to this Hermitian structure. So the Hermitian structure can be then twisted back to this, but the connection will change. So in other words, we can vary Hermitian structures. So another one of the problems there is existence of Hermitian structure on a bundle, such that this Hermitian structure actually is Hermitian-Einstein. And so here, this is what I would like to consider. I think about all such Hermitian structures. So I fix my homomorphic algebraic bundle. And now for any Hermitian structure, Hermitian-Einstein or not just Hermitian structure, I can think about the following number being computed, j of h prime, which I define to be the integral over x of the size of k, which is that same mean curvature squared, and then n, where here this squared is the trace of kk. Okay, so here h prime varies, the homomorphic structure is fixed. And now for each Hermitian structure, I have something. So I have a functional on the space of Hermitian structures, and then a theorem that this functional, not just it has critical points, it has the absolute minima at the Hermitian-Einstein structures. So J attains the minimum at the Hermitian-Einstein structures. So in other words, those Hermitian structures for which the Chern connection is, with respect to this homomorphic structure, is satisfies the Einstein condition. And still that's not illustrative enough. Then there is another action. If this is not illustrative enough, let's call it I of h prime, which is the, again, integral over x. And this time I take the curvature itself, omega n. So this is, of course, well, has something to do with Young-Mills theory. And now the important fact or theorem is that if I compare these two actions, then this is constant. And moreover, this constant depends only on the dimension of x, the class of the Keller form, and C1 and C2 of E. So it doesn't even depend on the holomorphic structure that we have on the bundle. So in other words, this justifies why I will be calling this the gauge theoretic side. Okay, so this correspondence here is of course something that is already very exciting in its own right. Have algebraic structures here, have connections, gauge theoretic structures here. That's already interesting. So whatever happens on one side can somehow be migrated to the other side. So what can happen on either side? So we started at 2:10, and this is it one long talk for 2 hours, or is it with a break in the middle?
Take a break.
How long do I have for the first half?
Oh, let's say until 3.
Until 3.
It's partly up to you. Not so.
So it's not fixed. So I can go on like this, and then when I say I'm tired, we're done. Okay, cool.
At some point, approximately in the middle.
Approximately, we should say. Okay, good. So I will keep that in mind. Okay, so now what I will be doing is I will be saying that there is something that comes from the algebraic side, something comes from the gauge theoretic side, and they travel through the correspondence, and then good things happen on the other side when the travelers arrive. So first I'll start on the algebraic geometric side. So if you want to parameterize this space here of Hermitian-Einstein connections, then you need to start with infinite dimensional manifolds. Really big. They're modeled by global sections of forms. Then you have these important operators, and then you take care that your complexes are elliptic, and so on and so on, and so that you produce something that is actually finite dimensional. So anyway, it is not so easy to understand the global structure on this side. On the algebraic geometric side, in fact, one can have a very explicit construction with equations. So I actually once had a master student trying to write those equations, and he almost did. So here I will describe this, and again, the way it is described is it's more interesting because it allows also to understand the additional structure it has. So on the algebraic geometric side, first we have an explicit description of the moduli space. And when I say moduli space, I don't mean a space literally, I mean a stack. Because here, of course, there will be non-trivial stabilizers, even if we have stable objects, because you can always rescale the thing that you have. So what we have here is the following. So this construction goes the origin of that is in the work of Grodnik in the 50s and 60s, and that is that given let's say a sheaf E on X. Now I think about E as being algebraic coherent sheaf or bundle. That now it doesn't really matter if it is coherent or not, because we're on algebraic geometric side. Then twist. So take E R with R high enough such that it is globally generated. And then, because it is globally generated, then you have the sum of the structure sheaf of X, which is the dimension of the global section of ER, mapping surjectively onto ER. Now, that might not, usually it will not be enough. You need to twist some more. So that the kernel F, let's call it R prime. So I twist in addition here by R here, an additional twist R prime is also globally generated. And then if I look at the global sections over X of F R mapping into global sections over X of E R plus R, then here I have that this inclusion, and these are vector spaces, is enough to completely classify the quotient. And so that means that to parameterize the quotient enough to consider the Grassmannian, well, let's call it Km, where this is dimension K, and this one is dimension M. And so there's this result from the 50s by Grothendieck. That this gives us an embedding of the chord scheme into the Grassmannian. And then, of course, if we start with any sheaf applied to E itself, then sorry, that's not E. You should have stopped me. It's let's call this O like this. This is O. Okay, so I'm looking at the subsheaves of this. So the quotient here that I have will be, each such quotient will be a point in the Grassmannian. So this realizes, so this realizes is as subvariety, an algebraic subvariety in the Grassmannian Km. And now the question is how many is, so how many of those bundles? Well, all of them that matter, and that will be determined by the Hilbert polynomial, is with a given Hilbert polynomial. All right. Okay, so that is not quite equations yet. And if you can see, if you look at the paper by Grothendieck, he doesn't produce a way to give equations. He just shows that some of them will be appearing there. So it's algebraic, but not explicit. But then there was this in around 2000, a work by Jokan Fontanian and Kopranov. That actually produced this this equation. So instead of taking only one twist, we take a sequence of them. So take E P plus 1, E Q, long enough, far enough and long enough. So Q is larger than P, larger than 0. And in fact, using this, forgot the name, Castelnuovo-Mumford things, you can compute good bounds, how far you should go. Then you can realize this inside the direct sum, or direct product, sorry, of the Grassmannians. And there, the canonical bundles will allow you to write equations explicitly. So then realize the chord scheme inside the product of Grassmannians K1 and 1, or M1. Sorry, not 1, J, and J is from P to Q. And the way it works is that on this product, we have the external sum of the canonical bundles, and then we can multiply them. So if we take not canonical, tautological, yeah, let's call it T, T, K, P, T, K, TP, TP, and TQ. Let be the tautological bundles. Some of them, then they sit inside the sum of all possible, and then we have the action of the homogeneous ring on this. Let's call this T on T. So to have this action gives us the equation. So in other words, this sum of tautological bundles sits inside the sum of the corresponding trivial bundles, which are just the pullbacks of sections of this. So T sits inside the trivial bundle, which is or the Grassmannian. And here I have this the sum from P to Q. And now here we have an action of this A. The homogeneous ring of polynomials on this part. Here we don't have a priori, but then when we multiply T by this, then we land in, let's call this S, land in S. Then we can go to S divided by T, and vanishing of this projection is exactly what gives us the equations. So that was the idea of Chekhov-Newton problem. Okay. Now, this is, of course, a moderately explicit way of producing this moduli space. And we never, not quite, but in this case, still will never quite get out of the world of varieties of finite type. But what is even more interesting for this talk is the fact that this moduli space is immediately derived, or you can derive it. So this is not a trivial question. So this was one, the explicit description. Which one? This one or this? This, yeah. Yes. Yes, it is this action on the space of Hermitian structures. If you look at all possible Hermitian forms, on each form, for each form, you have a number.
From this Wittgen's correspondence that you wrote down over there, E comma H goes to
I don't see it anymore, but
middle part, bottom part.
Yeah. You mean this one? Yes. So yeah, exactly. So if I choose H, so you can put H prime here. If you choose H, you get the Chern connection, and then K will be corresponding to that. Yes. So that was your question. Yeah. So in other words, here there is this almost one and the same object, Hermitian connection, Hermitian structure and the connection. If you have a holomorphic structure and Hermitian structure, you have the connection. If you have Hermitian structure and the connection, you have immediately the holomorphic structure. So if you have one Hermitian structure, you fix it, and then you start varying the connection, you vary the holomorphic structure. If you so you can travel in this triangle as much as you want. The important part, of course, is in that theorem that that was there at some point, is that if you have a holomorphic structure which is stable, can you construct a Hermitian structure that would be Einstein-Hermitian? That is hard. So one of the hard. So the other one is the injectivity. So there are also some vanishing theorems. But so in other words, Hermitian structure and Hermitian connection are almost like synonyms here. It's similar in a way to Levi-Civita connection, right? Okay, so as I said, that was part one of what we get from algebraic geometric side, namely the explicit construction and moreover, not only just the construction, but also the compactification, because here we have projective schemes and they're proper, so everything is immediately compact, so there's no issue of running away from bundles into something that we need to take care of. But another thing that we have here from algebraic geometric side is the derived version, derived structure. So here, of course, we have this correspondence, which is not on the nose, not an equivalence, but leads to an equivalence between coherent sheaves on X and homogeneous modules over this A, which I remind is all possible sections of the structure shift. Now, of course, on the nose it doesn't work. We have plenty of modules there that, for example, they are the only of finite dimension that corresponds to zero coherent shifts. But if you look at the stable ones, in a technical sense, the ones that so in other words, this sits inside as a, I always forget, reflective or co-reflective subcategory. And then what we try to do there is we say, okay, so if we want to classify all possible coherent shifts with a given numerical data given by Hilbert polynomial, then we are looking at the equations are given by action of a star. And then let's look at then actions up to homotopy. So let's look at A infinity modules of a star. So from here we go to A infinity, or let's put it this way because it's very different, A infinity modules over a star. So as before, it will be then here I will have T trying to be an A infinity submodule of this module, which is S. So S is naturally a module. T wants to be is a subspace or graded subspace, so it's one subspace for each degree of homogeneity. But then T is not necessarily a submodule. If it is a submodule, then we found a point inside the chord scheme. If we found a point, then we can start looking at the infinity structure, and then that gives us a derived structure. And again, that was the idea of Ciucan-Fontaine and Camprano. Well, this is an associative structure, and in that sense, it is an infinity. So here you have, I want T to be a module or submodule of S. S is a module over a star. Okay, or if you want a star, so it's really all possible sections of S. So this is a graded module over this graded ring, and I want to have T to be a graded submodule of that. And then I'm starting to classify all of them. There are some issues there, how to do it properly, but it can be done. Everything is settled. And now the question is, well, what will be the derived version? The derived version will be to classify all A infinity submodules. And it turns out that it gives the correct tangent complexes. So the result of this, and again, this is all due to Ciucan-Fontaine and Kapranov. I will not write, it's a very long double name, triple actually. Again, I wrote it before. So here, what the result here is, in fact, a DG manifold, not a derived scheme, but a DG manifold, which is a quasi-projective variety with an enhanced structure sheaf. Result, a DG manifold. And by that, I mean a quasi-projective scheme. Well, in this case, it will be actually projective. All right, a projective scheme. A smooth projective scheme, that's important, otherwise, why derive? A smooth projective scheme with an enhanced sheaf. Structure. So what does it mean? So usually if you have your moduli space, then you have the structure sheaf of this moduli space. M will be not smooth, and dimension will be hard to understand, and so on. So from here we go in this way to a projective scheme. In fact, here it will be explicit. It will be exactly the product of those Grassmannians. So let's call this the Grassmannian in the PQ range. And it is very explicitly given Grassmannian projective scheme, PQ range. And now then you'll have the structure sheaf of that as before, as usual, of this product of Grassmannians. So you can embed it into projective space, you have it there. But here now you will have grading. Well, it will be actually non-positively graded, and together with a homological differential, which this one has degree +1. So it goes always from smaller degree to a larger degree. So it is really in that grading that you expect in a good situation for derived geometry. And the important part is that the tangent space, the tangent complex, will be exactly the X complex for your structure sheaves. So will be correct with the expected, because there is no correct tangent complex. So that is actually quite important, the fact that it's expected. The correct tangent complex, that has the following corollary from this result, is that this modulus, this DG scheme, let's call it D quad. So D quad has a natural embedding, a natural map into the stack of all perfect complexes. As a natural map, or admits a natural map into perfect complexes on X. Yeah.
Over the global section structure of X, right? Because these
The not just global sections, the twisted global sections. So the homogeneous ring. Yeah, so I'm parameterizing coherent shapes on X, right? And now I'd like to have not just the classical points, but also the derived ones. So I need to, first of all, to do that, I need to understand what is the derived problem. So if you have a moduli space, classically, you do not automatically have a derived moduli space whose truncation is this. You can have plenty to choose. So here, this is a construction, a specific construction. And the point here is that the tangent complex is the expected one. So the dimensions of the cohomology of tangent complex will be exactly the dimensions of the X spaces. Yeah, so this extra structure comes from this solving. So I skip over this because then I will not finish at all. So the important part is that, sorry, did I answer your question? The important part is that not only that in this natural map, it also factors through the group that here, the group of symmetries that we have, namely the choice of this map. Remember that when we started by twisting, and then we chose the map from the sum of, so it was GL not R. T. C, where T is the dimension of gamma of X of ER. So remember, I twisted. I started by twisting, so this will be globally generated, and then I projected onto it out of the trivial bundle of rank exactly this. But this projection has, of course, you can act on it, and now this is exactly the freedom that you have. And now, if you have this map, this is it out. Is that how you write it out? Okay. So the important consequence of that, and then we'll have a break, is that another consequence. So if we suppose, and this is the main part, also was in the name of the top of my talk. So assuming, so far, notice that I haven't assumed anything about X except being compact and Keller, and with Keller class being integer. Now, assuming X is a Calabi-Yau n-fold, here on perfect X, we will have a 2 minus n shifted symplectic form. So there is 2 minus n shifted symplectic form. And that means that I can, because this is a tau, I can pull it back. So this one has this form, has this shifted symplectic form as well. And so this is a very concrete construction, and it's more of a proper scheme. It's a proper DG manifold, which is in very, not just derived manifold. Derived manifold, not every derived manifold is of this type. So this type of what I wrote here is a special kind of derived manifold. It's like a projective kind of derived manifolds. So this is what can be embedded into projective space. And so in other words, this corollary here says that, in fact, this one, if you don't divide by this group, you can embed it into projective space. If you divide by it, then you will get also a shifted symplectic structure. Now, this is, of course, a stack. Because if you divide by it, you don't really divide by it. So you need to look at this as a stack, because there will be non-trivial stabilizers for every point. So this is what algebraic geometry brings. And after the break, I'll talk about what we can try to have from the gauge theoretic side. Okay, so we are back. So now I will move to the gauge theoretic side. Okay, so on engage theoretic side. So here I will start making more assumptions about the manifold I have. So now X will be not just a projective, smooth projective variety, but it will be also of dimension 4. And Calabi-Yau is a projective, is a Calabi-Yau fourfold. And because it's a Calabi-Yau, I will have the top holomorphic form omega. And now, since we are on the gauge theoretic side, I'm looking at the modular space of Hermitian-Einstein connections on a fixed bundle E with a fixed Hermitian structure there. And remember, I said that it will be important to have the first term class vanishing. So that's what I require now. Okay, so then I would like to classify them. So this will be connections. Such that when I look at the Hermitian connections, I will not write it, but I will always mean that all of the connections I'm considering here are Hermitian, such that the curvature, if I look at the curvature, then because we are on in particular Keller manifold, we will have the primitive part, sorry, the form part, then the antiholomorphic part, sorry, the holomorphic part and the antiholomorphic part, and that is required to be 0. That's what it means here to be Hermitian and Einstein. So where is Hermitian? Where is Einstein? Can somebody say? Tell me, where is Hermitian? Where is Einstein? Which one is Einstein? Okay. Which 0? There are 3 zeros. This 0, this 0, and this 0. Which one of them is Einstein condition? This one. Yeah, precisely. So remember that the idea was that the curvature will be anyway. That's where it comes. And here, of course, there's 2 parts. One of them is because it has to be churned, the other one has to vanish because it's Hermitian. Okay, so here then what was realized by Donaldson and Thomas in 1998. Well, it was realized before, but they proposed something to do about it. So Donaldson and Thomas. And they said that, okay, so here we have too many conditions. We need to reduce them. So use the form, so the metric and the form together to introduce, to have this, just like for, in analogy to the real case, to have this endomorphism on the 2 forms, and then split, and it squares to 1 to split 2 forms into dual and anti-self-dual, and then we'll have F2 F omega being equal to F20 plus being equal to F02 plus being equal to 0. So the split into self-dual and anti-self-dual connections. So the curvature take part in the self-dual and anti-self-dual parts of the 2 forms, and then we take only 1/2 of the curvature, namely here, this one, not quite 1/2. The stability condition still remains the same. So we still want to have the part coming from the Keller form, but the self-dual parts have to vanish, only them, not the anti-self-dual. And then you will have just enough equations as variables. So then it becomes a determined system. And so that was in the same paper where from which that was related to the PhD thesis by Thomas, and then from which Thomas invariance for Calabi-Yau threefold came. That was the first part of the same paper. This is section 3 or 4, I forget which one, maybe 2 of them, 3 and 4. Okay, so that was their proposal, and then something around 10-15 years ago, Dominic Joyce had this idea. Around that time, around 15 years ago, this paper by PTVV, Pantepto and Metsozivake, appeared with shifted symplectic forms that I mentioned here. And so, of course, this pairing that we have using those, this is not just a pairing, this extends to quite a lot of things. It's exactly to this symplectic form. So then to take the splitting on the algebraic geometric side, use this splitting on the algebraic geometric side. Okay, so that means that what we need to do, well, in the way that Dominic had the idea, is to split the abstraction bundle. So there, what we have on the algebraic geometric side is, if we look at the moduli space, then we have the group GL of some dimension acting on it. But this moduli space has the classical part, has the abstraction part. So here you have the 2 sections here, and you look at the places where they are equal. And then you have also here something else. Well, if you want to have it, you can complete it to a simplicial diagram. So this is the abstractions, so the relations between relations. And then you'll have also M3, but M3 and GL are paired together. So these 2 things paired. This also are paired. And here you have pairing given by this shifted symplectic form. So here it will have -2 shifted symplectic form. Shifted symplectic form gives, well, because this is in degree 1 and the form is graded antisymmetric, it gives us not antisymmetric but symmetric form here. So gives eta here a symmetric 2 form. Okay, and non-degenerate type, and C-linear, it's not Hermitian of any kind. Okay, so that pairing then extends to a series lambda n, so this is n2, 2 plus n, n minus 2, n, and starts from 2. So the first one is the pairing, and here you have this entire tail such that this is actually what is called shifted symplectic form, explicitly written. So it's a power series, formal power series, such that it is a cycle for the combined differential, which is the RAM and homological differential. So this is just the beginning, as PTVV called this. So this is the form, and the rest of them are keys. So this is not closed, but it becomes closed when you add the keys to this form. Okay, and so the idea of Dominic was to split, just like this, split M1 into M1 plus, and then, well, actually, M1 projected into M1 minus, such that this projection, well, actually, I can probably write it because it's a bundle. I can actually write it as a split, M1 plus and M1 minus, and such that then throw away the plus part and look only at M0 this. And that will be a perfectly obstructed moduli problem, or in other words, quasi-smooth. So in other words, we can then produce a virtual fundamental class. Just like for moduli space of Calabi-Yau 3. Because the action of the group is important, but it was ignored at that time. The important part was actually the splitting, and here there is an important nuance. This splitting here is so that splitting is not C-linear. It's only R-linear because it depends. So it is really it doesn't respect complex structure. And if you choose a different topolomorphic form, you'll have a different split. So this splitting is only R-linear. And in fact, there's a nuances. There is one and there is two. Is that when we want to split it in this way, then these parts have two conditions, not one. One of them is that, so the reason is that this form is C-linear, so it breaks into two R-linear forms, the imaginary part and the real part. And then the splitting should be that both of them are Lagrangian with respect to, say, imaginary, and negative definite with respect to the real. So two conditions. Lagrangian with respect to the imaginary part, and negative definite, if I want to get this, the minus, with respect to real. After all, if we start with symplectic forms, we might as well have something to do with Lagrangian things. So this is Lagrangian. The idea was Lagrangian only with respect to the beginning of the form, to this the two form, not the tail, not the keys. Anyway, that was the idea. So you can summarize this idea in very simple ways. It looks complicated, and it's better than not to really to think about it too much, because there's a better way to say it. Well, let's just have a proper Lagrangian foliation. So instead of putting all those provisos, let's have a proper Lagrangian foliation. So let's call it, this is like in computer science, it's the beta version. So the actual version that comes out is so the marketing version, or the next version. So have not just splitting with respect to this part like this, but splitting with respect to the so in other words, have an isotropic structure as well. So take construct a Lagrangian foliation on M. All of them. So in other words, what is the difference between splitting and Lagrangian foliation? So this foliation means that it is splitting plus isotropic structure. Okay. If you take just a splitting, you can construct the base. You can divide by it, but that's it. That's what you need, and that's what Dominic actually wanted. He wanted to construct. So that construction what came out in the paper by Dominic and myself. That's something about invariance, visual implemented classes for moduli space on Calabi of 4 folds. But now, if you put isotropic structure, that is an extra thing on this foliation, and then it was constructed. Moreover, it was constructed not just for a manifold; it was constructed including the group actually. So here was the result by me, Lyudmila Katsarkov, Artan Shishmani, and Chintu Yao. So there is theorem. So there is not just locally, globally defined. Foliation on this derived quad scheme of X divided as a stack by GL, whatever GL was. I forgot what did I write GL, but anyway, T. So this is a stack, but only on the stable part. So the part where you have the same, just the number, so just the multiplication by constants at each point. So that's the stable part. So there is a global derived foliation there, together with an isotropic structure with respect to the imaginary part, and such that when I look at the real part of this symplectic structure, of the sheeted symplectic structure, then if I look only at the cohomology, the action on cohomology, which means that I really now take only the second part because I look at how it acts on cohomology, then this is negative definite. On the foliation. Okay. And now this has a consequence that is important. Namely, that we can divide by this foliation, and we can reproduce everything back by taking critical locus. Well, I think about, you probably can formulate that as well. I think about a stack as a simplicial diagram of schemes, because this is not just any stack. It's a very simple kind of stack. It's an action stack, right? So you have the group acting on, so you take the nerve of this action. And so everything essentially happens, everything that you care for happens in the simplicial dimension 0 and 1, right? So the actual manifold, the G manifold, and the G manifold times the group. And now you have the foliation on the simplicial dimension 0, and then it extends, so it is equivariant with respect to the action. So in other words, it survives to the entire simplicial nerve. So I don't need to. So I would try to be as explicit as possible. So the DG scheme is explicit almost down to equations. The group is obvious, and then what is not explicit is the construction of this foliation. Actually, I can erase here because it involves the construction of this sheaf of all such foliations and proving that this sheaf is soft. And then locally, it's trivial to show that it exists, and then it has to have global sections. And because it's already happening on something that has a topological base, it's not just some abstract stack. It actually has a scheme, projective scheme, the product of Grassmann. So then you can immediately say that you can have sheaves there. On.
So this is a derived scheme. What kind of built foliation would derived require?
In what sense? So it is a so if you think about so if you have a tangent complex, right, and you have so the best way to do it is kind of a slightly abstract, but you have this map into I always forget this algebras that have two gradings together. The way they all yes, mixed graded. Thank you. Mixed graded algebras, right? So if you dualize it, this dualization is not always an equivalence. Then you can think about this as the DG Lie algebroid mapping into your tangent Lie algebroid. But it's again your tangent Lie algebroid is also DG Lie algebroid. If you don't dualize it, then you have mixed graded structure. You have the drum complex, and then you have another one. You map into it, and that's so in that sense there is this paper that appeared after all of this was written by Toyn and Vitsozi, where they show what it means to have foliations in derived algebraic geometry. And in fact, after their paper appeared, we rewrote ours slightly. So we started using their notation. So we put a new version. So the fact that here we have this the structure is that we can actually take the quotient by this foliation. So corollary, we can take the quotient by this foliation and obtain something that is very explicit. Obtain that base manifold that we started with, product of Grassmannians. So this GR PQ with derived structure. No, sorry, just it as a manifold, as the base. Only one bundle, half of what we have as the abstraction bundle. Let's call it E minus as the abstraction bundle. And that will be the quotient, together with a section of the dual bundle, which is canonically isomorphic to E plus, because we have this pairing that is canonically depends. So this here depends on the symplectic form that shifted symplectic form that we start with on this eta. So given by eta. And let's call this a section nu. And then the original stack will be the derived critical locus of nu. So critical or d critical of nu is the original stack. So meaning that. Now this corollary is not immediate. There is a fact that allows this corollary to follow immediately. Because this fact that we can take the naive quotient and get the categorical, so the derived categorical quotient, well, that follows simply because there is a statement, I was discussing it with you, that there's the statement also in that book on this 2-volume book somewhere, I forgot exactly where, that says that if you have the correspondence in the classical parts, then that works well. So the naive quotient will be it, or maybe it's not written explicitly, but it follows. Don't remember. Okay, so because you always give me this look when we were talking this morning, and I thought maybe I don't have a book with me, so maybe I imagine it. Okay, so why is it so? Well, here we have a fact that allows this corollary to follow, is that because we have negative definiteness, it immediately tells us that the number, so the classical scheme, the what's called the coarse scheme for the before the splitting and after splitting doesn't change. In fact, because of negative definiteness of the this, because of this, the fact that the real part is negative definite on the part that remains, the real part of the symplectic form is negative definite on E minus. Because of this, the reduced classical part is the same as before and after the split. And the reduced classical part remains unchanged. Okay. Now, so this is already some interesting, nice consequence of having this correspondence, this Thomson-Michiao correspondence, that tells you that if you do something on the gauge theoretic side, you can bring it to algebraic geometric side. Here you can split things. Yes, you can get something that is not really algebraic because it is C infinity. It is not even over complex numbers anymore. But you have something that is well, that's obviously has some contents. And moreover, you can reconstruct this thing back. So what is especially interesting here is this very simple structure. You have a very classical finite dimensional smooth manifold that is explicitly given. You have some, complicated bundle, again, of finite rank on this manifold. You have a section of that that gives you the moduli space after the splitting. Then you have a shifted potential whose critical locus gives you this complicated thing about every modular action of group. Yeah.
Is there something on? Is there some structure on this that lets you reconstruct the thing as a complex or an algebraic variety?
Good question. I don't know yet. That's one of the things that's one of the reasons I wanted to go back, because you see, one of the things that I still couldn't understand. I'm trying to, maybe it's just my ignorance. I don't know in this DUI correspondence, what is the role of complex structure? Real structure is there, but because this, you can see that this is just, so far, this is mimicking of gauge structure, right? Of gauge theoretic side. And the window through which, or the door through which we go back and forward doesn't allow complex numbers through, at least as far as I know. So I wonder. So there must be something that is interesting. I just didn't get there yet. But instead of doing trying to guess what is here, what I said, okay, so we got quite a lot from gauge theoretic side on the algebraic geometric side. Let's try to move algebraic geometry on the gauge theoretic side. So this is what I'm trying to do in the last 10 minutes. Okay, so let's then try to do what to move to bring things back, and so we have a contribution from the gauge theory by splitting there. Let's move the derived version to the derived structure, because here the situation is so simple. Can we try to reproduce the same kind of there? Because somehow the idea came from Donaldson Thomas paper. Let's see what was the idea. So the idea, of course, is based on this exceptional isomorphism, namely that if you take SU4, then it is isomorphic to spin 6. And spin 6 sits inside spin 7. Okay. Now, if I have my Calabi-Yau fourfold, then we have the holonomy group being part of SU4. So then we have action of SU4 on our forms, and then we can start trying to see the splitting that we have. But in this case, we also have the action of spin 7. So two forms split under spin 7. So if I take all two forms on my Calabi-Yau fourfold, then I split into one, which is the adjoint representation, as is always there. This is something that there's this paper that I really like by Conan Leung from about 2000, where he shows how this adjoint representation, well, he doesn't show, he just explains that it should be. What the consequence of that? That adjoint representation appears all the time that we have holonomy. So this is the holonomy representation of spin 7. After all, that's the dimension of the group, plus another part, which is the 7-dimensional part, because this is, of course, dimension 28. Now, if we took, so this is the real splitting. If we take the same splitting, but now for spin 7, So this is spin 7. If we look at spin 6, which is the same as U4, then this part splits further into this real primitive part, but real primitive part, plus something B. So this splits into this. This is again adjoint representation, dimension 15. So here I write the dimension 21, 7, here dimension 15. Oh, this is of course then dimension 6. Now this one, again under spin 7, splits also into two things. The Keller form, and then something else. Let's call it C, dimension 6. And in fact, even in that paper by Donaldson and Thomas, and they attribute that idea to Dominic Joyce back then in '98. He was already then, of course, in Oxford. That's this splitting that I wrote, that one, corresponds to allowing the curvature. So the Hermitian-Einstein means that curvature is all inside here. Is in here only. So if you have any curvature, it's there. Outside of this, it has to be 0. If we have not Hermitian but spin 7 or spin 7 instanton, then the curvature can be allowed to be outside, namely in this 21. Is in 221, which is bigger, okay, by dimension 6. And by the way, you can check that, of course, these ones are also dimension 6. And it turns out that, in fact, it is this one that is still has to vanish. Okay, so in other words, we go from SU4, and here I write it as Lie algebra, SU4 connections to spin 7 connections. By the way, I have 7 minutes left. How far can I overdo?
Not sure. I make it fast.
So none, not at all. Okay. So until the break-in. Okay, but do you want me to stop on time or
Probably take
a few minutes? Okay, because I didn't plan. I had 2 hours and it was not. Okay. So now I switched to Lie algebras, and for the following reason, because I would like to somehow to really take care of connections in an algebraic way. So again, we have our EH. And from that, what I would like to do is to go to the Atiyah Lie algebroid corresponding to this. I will denote it by this, A of E. I will omit H because sometimes I will really not care for H, sometimes I will. I suppose Atiyah algebroid is familiar? Okay. And so then I would like to see connections as representations of the tangent Lie algebroid there. And I take tangent X mapping into Atiyah Lie algebroid of E. The only problem is that it is not. What bothers, what breaks here, what stops it from being a representation, namely that curvature. And so then again, there is a paper by Kapranov, I forgot the year, that allows you to start with any Lie algebroid and produce a free Lie algebroid. Free Lie algebroid FTX. Now, the idea is that it is free only on the bundle itself. So it's, if you think about forgetful functor from Lie algebroids to tangent to bundles, then you can go back. That's the construction. And
Bundles over the tangent space.
no, bundles over the X. So you have a bundle, let's say. Ah, yeah, with the anchor, yes, yes, of course. But here, yeah. Sorry, I misunderstood what you said. Yes, so I was fixated on what I was trying to say. So you start with the bundle Tx, and then of course Tx maps to Tx, and then you go up and you have this this thing. So you have the anchor map is there, and then of course you have any connection is given as a representation here. Now the thing is that of course that gives you any connection. Question is what would be how curvature will appear. Well, this is filtered. It is not graded, but it is filtered. It starts being constructed as a graded object because you take freely algebra, but then you divide by relations, and they are not homogeneous, so it's filtered. But there is one. So this part, the lowest part in the filtration, is very nice. Namely, if you look at the lowest part of the filtration, so let K, like this, has nothing to do with the previous K, be the kernel of this map at Tx. Then this is also filtered, and then the lowest part of the filtration is it's growing filtration is the square of Tx. So in other words, if you have a representation like this, then you have the penetrating square sitting inside here. It is mapped here, and that is the curvature. So curvature is encoded inside this representation. And now you would like to limit this curvature. And now the way that curvature is limited in all of the structures, and again, refer to this paper by Conan Leung about the metric division algebras and how this it appears there, is that you choose a particular space, namely the adjoint representation, and you say that curvature is allowed to be only there. If you take curvature as being with values in forms. So then restrictions of curvature. For example, you can take the 21 sitting inside the two forms, and you say you want curvature to be only there. So you can go from that to the dual inside Tx, so just with respect to duality. And this you can use to create an ideal. So this generates an ideal inside the Lie algebroid. You divide by it, and then you obtain an ideal. Let's call it I, f Tx. You divide by I, and now let's call this the Lie algebroid given by this 21. So now you have this Lie algebroid that you can ask what will be the home of this Lie algebroid into the Atia Lie algebra of E. But now this is, of course, this is not a finite dimensional space. This is infinite dimensional space with topology and all. This is as well. So this is, in fact, is an infinite dimensional manifold. And if you want to look at this as a space, you need to take the derived version of this space. So you take now resolutions, three resolutions of this, and take the usual simplicial resolution of that. So you take 3 of L to 21, then 3 squared of L to 21, and so on. And now you have home into A of E. And so now what you have, so this is home. You take apply home factor from here to here, from here to there, and so on. And in this way, you'll get a co-simplicial diagram of infinite dimensional manifolds. So that would be your derived manifold of connection of spin 7 connections. So gives you is a derived space of spin 7 connections. Of course, you need to divide by the gauge group. So here it will be actually a stack. And now the important part that I need to get to something that's a theorem that I would like to formulate. And that should be the last. Maybe if somebody comes in, I still have 2 minutes to finish. So if you take this derived moduli space and call it M, in this case, spin 7, then if you look at corresponding MSU4 and you divide by the automorphisms of EH, so this will be a stack, infinite dimensional simplicial stack, and then this would be a derived critical locus of a potential, or the derived, of a shifted potential, of a -1 shifted potential on, now you take the moduli space now of the same kind, but now of that spin 7. And again, you divide by the automorphism of EH. And so this is a theory. So why can I do that? I don't even have Calabi-Yau structure. I mean, yes, I do assume Calabi-Yau structure on X, but I don't have any shifted symplectic forms. At least I'm not aware of a theory of shifted symplectic forms in this infinite dimensional things that are not algebraic or any out. So I don't even know what would be the, say, Grothendieck site there, or derived site.
Are the quotients finite dimensional?
No, nothing here is finite dimensional. But the point is that all the tangent complexes are elliptic complexes. So yes, you can eventually get to finite dimensional complexes. So they will be. So they are secretly all finite of finite rank or finite type. It's just the way they are written, they are infinite dimensional. Yeah, but they are given, they naturally appear as infinite dimensional simplicial manifolds with the action of this, again, infinite dimensional groups, because these are not just groups, they are functions with values in groups. So this is enormous spaces divided by enormous groups, but there is a natural way to pair them because they come from the structure itself, namely coming from all of this construction there that was already in the paper by Dons and Thomas. And the fact that it is a critical locus immediately tells you that you have a shifted symplectic structure without any theory whatsoever. But this is...
So it's a base by this the thing that...
Well, it is infinite dimensional the way it's...
But when you take the tangent
yes, because it is that same determined problem of spin 7. So this fact here, the base, where is it? Spin 7. Here you have, if you believe, so this I need to check. So there's no notion of quasi-smooth for these dimensions, but if you divide by...
Take the corresponding tangent space. That's some complex of infinite.
Yeah. It will be exactly the complex that you expect on algebraic geometric set. So it's so in terms of depth of complexes of tangent complexes, yes, it is.
That's all I mean by quasi-smooth.
Yeah, exactly. So I was saying that can you present it as a finite dimensional manifold with a finite dimensional finite rank bundle? I think so. You just need to check. Okay, so I was actually planning to explain to give a simple example of how Delboca homology actually appears here in this language in a very nice way, but I had no time. So I'm out of time. I had